Right, alcohols. So in terms of priority, right, alcohols have the second priority, right? Second priority in terms of naming, and really that also comes down to bonding. So it's got the second strongest forms of bonds of the functional groups. So in terms of its general formula, it's ROH, yeah? So an OH attached to an alkyl group. In terms of its naming, right, it most commonly will have the suffix ol, yeah, unless coupled with a carboxyl group, right, in which it will have, the prefix hydroxy, yeah? So we could have, and so an example of that is that we would have, say, the difference between, let's go ethanol, whereas if I couple that with carboxylic acid, have that second functional group, this would be called hydroxy ethanoic acid, right? So the carboxylic acid has the highest priority. Yeah, so the number one priority in terms of naming, in terms of bonding, is carboxylic acids. Hydroxyl, yeah. So hydroxy. Hydroxyethanoic acid. Yeah, so the functional group is hydroxyl. Alcohol is the homologous series. So that's the distinction. I'll just add that to naming. So hydroxyl. Hydroxyl is the name of the functional group. Alcohol is the name of the functional series. Same thing with carboxylic acids. Carboxylic acid is the homologous series. Carboxyl is the name of the functional group, which we'll get to. Right, it's hydroxyl. The oxygen is attached to a hydrogen. So we're going to have hydrogen bonding. Yeah. And dispersion. So all of them have dispersion forces. So if we talk about, or if there's a question relating to describe the bonding within such and such a molecule or between such and such a molecule, you would state the most significant intermolecular force and dispersion. Or if it's just a non-polar molecule, it's going to be dispersion only. So hydroxyl and dispersion. Obviously, if I've got hydrogen bonding, it's polar and it's soluble within water. In terms of reactions, right? Yep. Well, because hydrogen bonding is a subset of dipole-dipole. So you don't specify both. Yeah? You wouldn't specify both, just hydrogen bonding and dispersion. Yeah? We treat hydrogen bonding as something different because it's more significant. It's stronger. It's soluble, types of reactions, right, undergoes combustion, right? We know that from bioethanol, and so in addition to combustion, but combustion is sort of given to any hydrocarbon can undergo combustion. You just burn it, yeah? Some burn more readily than others, right? But other than combustion, it also undergoes condensation reactions, right, with either another alcohol, which would give you an ether that's not described, not talked about in year 12, when I couple it in a condensation reaction with a carboxylic acid, will form the ester. Yeah, and also it undergoes oxidation reactions. And the product of oxidation is determined whether or not we've got a primary secondary or a tertiary alcohol. So let's talk about the differences between there. So a primary alcohol is a hydroxyl functional group where the functional group is attached to a terminating carbon. Or if we want to think of it in another way, to the carbon that the hydroxyl functional group is attached to is only attached to one other carbon. Yeah? So an example of that butan-1-ol is an example of a primary alcohol. Secondary alcohols, the carbon attached to the hydroxyl functional group is attached to two other carbons. That says other, by the way. Two other. So an example of that, butan-2-ol. And what do you think tertiary will be? 3, yeah. 3 carbons. So essentially, this when the hydroxyl functional group is attached to the same carbon within a chain that has a branch coming off it. So, example, meth and propan-2-ol. Yeah? So the products of oxidation of these compounds are different, and we'll explore that in the next topic. That's why we distinguish the difference between them. Okay, aldehydes. General structure, it's a C double bond O and a hydrogen, just that. Yeah. In terms of drawing the skeletal structure of aldehydes, you must explicitly show the hydrogen, right? Notice how in other skeletal structures you do not, but when there's an aldehyde functional group, because the hydrogen forms part of the functional group, it should be explicitly mentioned. Amides, yep, amides would be your C double bond O NH2. Yep. But I mention this because that hydrogen is attached to a carbon, not just the nitrogen there. Yeah. Well, in terms of naming, you don't need to name aldehydes, but just for your reference, it will have the suffix -al. So ethanal as opposed to ethanol, right? Ethanol, OH, ethanal is the aldehyde functional group. Now, what do you think in terms of intermolecular forces? Thoughts? Yeah, dipole-dipole. Why is it not hydrogen bonding?
Because the oxygen isn't with the hydrogen.
Exactly. So dipole-dipole and dispersion, not hydrogen bonding. Now, it's a hydrogen bonding acceptor, but not a hydrogen bond donator. So it can form hydrogen bonds with water, so polar and soluble. Yeah, it can form hydrogen bonds with water, but not with itself. Yeah. And in terms of reactions, we don't need to worry about reactions. Aldehydes are a product of a reaction, which we will explore, but not reactions of aldehydes. Ketones is a C double bond O within a chain. Yeah. Again, not something you need to name, but it will have the suffix "-one". Oh, I didn't give you an example. So an example, that would be butanal. An example of a ketone, just do a simple example. I'll do the same, right? Same trend in examples. This would be butanone. We don't have to specify the number, right, of the ketone, because it can only come on one place. Yeah? Ketone won't be on a terminating carbon, otherwise we end up with an aldehyde. So that's the distinguishing difference. Aldehydes must be a terminating carbon. Same with carboxylic acids, must be a terminating carbon. If I had pentan, I could have pentan 2-one or pentan 3-one. In terms of bonding, similar to aldehydes in that it's dipole-dipole. And dispersion, it's polar, it's slightly soluble, and we don't have to worry about reactions. Aldehydes will be slightly more soluble than ketones and will have a slightly greater boiling point as well. Right? And that's because those terminal functional groups, right, greater access to that electronegative atom, and therefore that's why the bonding is stronger. When I move that functional group or move it more towards the center, we increase the level of symmetry. Less access to that functional group decreases the level of bonding. So if we're decreasing the bonding, we're decreasing both the boiling point and the solubility. Carboxylic acids, right, I've seen those before. C double bond OH, carboxyl functional group. In terms of naming, it's got the suffix anoic acid. And one of my most hated substances to work with. Is this. Butanoic acid. Reason I hate working with it is because it smells like vomit. Yeah? Comes also called butyric acid. It's the acid which is formed from rancid butter. Butter in which that goes off. Now, in terms of bonding, right, we've got a hydrogen attached to an oxygen, so we've got hydrogen bonding that can form. Not only that, we've got multiple hydrogen bonds that can occur. Right? Reason being is that I can form what's called a dimer. D-I-M-E-R, dimer structure. So there's multiple hydrogen bonds. So very strong, So carboxylic acids, in terms of the trends in our boiling points, will have the highest of the boiling points for similar length hydrocarbon chains.